Next, we're going to talk about
the intermediate value
and
theorem.
we call that IVT. The intermediate value theorem, IVT. Okay. So first, take a look at this graph over here. This function f here is continuous on a to b, this closed interval a to b. You see that here and also here. Okay. And we let n to be any number between f of a and f of b. So to pick any number between f of a and f of b, with f of a does not equal f of b. So at this end and this end, the function value are different. Then what happened here is this n here is this intermediate value that we talk about here. So it's in between the function value at this two endpoint. Then there exists a number c in a to b, in this open interval a to b, which means c is greater than a and less than b, such that f of c is going to take on this intermediate value n over here. So that's called the intermediate value theorem. Okay. Now let's take a look at this example to understand what this theorem says. So Ln of x is continuous on this closed interval from -1 to 5. You see there's no break from -1 to 5. Okay. F of 1 is equal to Ln of 1, which is equal to 0. F of 5 is equal to Ln of 5. So f of 1 is 0, f of 5 is Ln of 5. Now I'm going to pick an intermediate value that's between 0 and Ln of 5. I'm going to pick 1 here as this intermediate value. Okay. By the IVT, there is the number c down here between 1 and 5, such that f of c is equal to this 1, this intermediate value here. Now what is f of c? F of c is just Ln of c. Ln of c is equal to 1, so c will be equal to e to the first power, so that will be equal to e. So you see that e is about 2.7. So there is this number here, which is this e, between 1 and 5, so that f of this c is equal to this intermediate value over here. Well, you don't have to pick n equal to 1. You can pick n to be any number between 0 and this Ln of 5. Then I'm guaranteed that you can find a number down here between 1 and 5, f of that number equal to that intermediate value there. Okay, so that's what the intermediate value theorem says. Now we're going to use this to prove this equation has at least one real root. Now what does root here mean? Think about it as solution. Okay, so that means it has at least one real solution. Now the idea over here is we have to make an intermediate value. So I'm going to move all the external to one side and leaving this number here 3 to the other side as that intermediate value. And we're going to let this f of x to be Ln of x plus x. Okay. Now the function, this function over here is continuous on, this is continuous on 0 to infinity, and this is continuous on all real number. So when you put them, when you consider both of them, then the function is continuous on 0 to infinity, not including 0. Okay. Now, this intermediate value here is 3. So I'm trying to find a function value that has to be less than 3. So I just try 1. So f of 1 indeed is less than 3. Let's pick another value for x, so that f of that is greater than 3. Well, I try 5. However, if you try e, that will also work. F of 5 here is greater than 3. It's greater than 3 here. So this f of 1 is less than 3, f of 5 is greater than 3, and the function is continuing on 1 to 5, the closed interval. So by the intermediate value theorem, there is a c in this open interval 1 to 5, such that f of c is equal to this intermediate value here, 3. So in other words, c is a real root of this equation. So we just prove that this equation, which is equivalent to this original equation, has at least one real root. Another proof here will be, now we're trying to prove this equation have one real root, one real solution. We can move every term to the left side. And now we're going to have a zero on the other side. We're going to use this zero here as this n intermediate value. And we let f of x equal to this. Now this function is again continuous on 0 to infinity because Ln of x, in order for Ln of x to be defined, x has to be strictly greater than 0. So that is continuous on this 0 to infinity. Now we try to pick a number here, so that will, the function value of that number is less than 0, and then pick another number here, the function value will be greater than this 0. So we try to pick 2x over here, so then the corresponding function value, one will be less than this intermediate value, the other one will be greater than this intermediate value over here. So I pick 1 and e. Now f of 1 is equal to -3, which is less than 0. F of e is greater than 0. So by the intermediate value theorem, there is a c in 1 to e, in between 1 and e, such that f of c will be equal to this intermediate value 0. In another word, c is a real root of this equation. And this equation is equivalent to this original equation. So we just prove that there is at least one real root to this equation. So that's the end of the proof.